Hello there, it's Protein Binding 3, continuation of my previous lecture, Protein Binding 2, in which I discussed about the types of plasma proteins and discussed albumin in detail only. So rest of the proteins I cover now in this video lecture. Alpha-1 acid glycoprotein is another important plasma protein other than albumin, which through binding also plays important function of transport. Alpha-1 acid glycoprotein is also known as mucoid. Its molecular weight is 44,000 daltons and its plasma concentration is 0.4 to 1% weight per volume basis, which is quite lesser as compared to albumin, which was around 3.5 to 5.5%. This is the structure of AGP or alpha-1 acid glycoprotein. On the screen, you can see the structures of both alpha-1 acid glycoprotein on the right side of the screen and albumin on the left side of the screen. And it can be seen easily that alpha-1 acid glycoprotein chain is less lengthier, lesser binding sites, and therefore, as compared to albumin, um, its molecular weight is lesser, which is 44,000 daltons, and in case of albumin, its molecular weight is 65,000 daltons. That's why albumin emerges as important protein among other plasma proteins. Moreover, it has a greater impact on the osmotic pressure as well as compared to other plasma proteins. The drugs which will preferably bind with the alpha-1 acid glycoprotein would be the basic drugs. Examples are propranolol, imipramine, and lidocaine. And among endogenous substances, corticosteroids bind with alpha-1 acid glycoprotein and it's being transported with the help of AGP throughout the blood. Lipoproteins is another important class of plasma proteins which are macromolecules. These are composed of lipids and proteins. These are of various types like VLDL, very low density lipids, and LDL, low density lipids, HDL, high density lipids. Now the structure, as you can see that there is an apoprotein layer as shown with the purple color at the outer rim of the molecule. Then there are the various types of lipids shown by red lines pointing towards the central part of the structure. And these are triglycerol, phospholipids, esterified cholesterol, and esterified cholesterol. Lipoproteins are involved in the transport of lipids and acidic drugs when albumin gets saturated. Now the RBCs or erythrocytes, which you know, very important proteins which constitute almost 45% of the blood, and these are also involved in the endogenous exogenous substances transport through binding. Drugs which bind to albumin also bind to RBCs as well, while few might preferably bind with the RBCs. And the examples of such drugs are like phenobarbital, um, amobarbital, and phenytoin. However, irrespective of the fact that how greater affinity a drug holds for the RBCs, mostly it will bind with the albumin first. But the drugs which preferably bind with RBCs, this binding will influence the drug distribution then. Total blood hematocrit will be determined in order to estimate the possibility of free drug concentrations and its distribution. More a drug is protein bound, lesser will be the unbound fraction and lesser distribution occurs. As protein bound drugs cannot diffuse easily or cross the capillary pores, so therefore their distribution will be lesser. We already discussed this concept, but here in the diagram you can see easily that albumin is of such a large size molecule that it cannot cross the capillary pores easily, and so it is true for the drug which is bound to the albumin, that if it is bound with the protein, it won't be able to cross the capillary pores as well. Volume of distribution is not only dependent upon the protein binding, but it is also dependent upon the lipid solubility or the drug's nature, whether the drug is lipophilic or hydrophilic. So, some exceptions to this rule could be present. The drugs which are highly lipophilic would be having a greater volume of distribution despite the fact that they are highly protein bound as well. When several drugs are selected from a single family with close physical and lipid partition characteristics, the apparent volume of distribution may be explained by the relative degree of drug binding to tissues and plasma proteins. This concept is explained in this diagram. Just imagine that these four drugs, 1, 2, 3, and 4, belong to the same class of drugs, and these drugs closely resemble to each other in their physical or lipid partition characteristics. So, supposedly, their volume of distribution should not be much different from each other. However, their capacity for protein binding varies, which results in different volume of distribution, despite the fact that the drugs belong to the same class and not they closely resemble as far as their physical or lipid partition characteristics are concerned, but their volume of distribution will vary based upon their different capacity of protein binding.